In this lesson, we'll talk about lung volumes and capacities, and also how to read something we call a graph we call a spirogram. So here are learning goals and key objectives we'll get through here. But before we talk about these volumes and capacities, we'll talk about something called spirometry. So it's actually a really easy procedure, and you can have one of these machines called a spirometer. There are different types now. They don't all look like this, but what a spirometer does is basically somebody breathes into a tube, and this spirometer is actually able to measure the amount of volume of air that's being breathed into the tube, and also how fast it's being moving throughout that tube. So it can measure breathing rate, like the pulmonary ventilation, the volume of air that's being blown into the tube, and also the airflow rate. And I love the way she's looking at him here, and she's also making sure he's doing it correctly, and also prompting him to and encouraging him to breathe normally, and also take a deep breath in, deep breath out, depending on what she wants to measure in this example. Now, it estimates lung size. I'll get to why it can't actually directly measure your full lung size in a few slides over here. And it can also measure your respiratory rate. We'll cover that at the end. So the overall goal of spirometry is to give you data about how much volume of air is moving in and out of your lungs. And here's a very short example of that we see from the OpenStax version. And what we see are all these volumes that can be measured from a simple spirogram, which is the chart or the graphical representation of the data you can get from a spirometer. Now, spirometry, and here's another machine right here. She's going to blow into that tube, and this machine is going to record the volume of air moving in and out of that tube over time. Now, why is it useful? Well, it's non-invasive. All you have to do is breathe into a tube. You don't need to be poked with any needles. You don't need to sit in a machine and have pictures taken of your insides. So all you have to do is breathe in that spirometer. Now, why do we use it? Well, things that this data can be useful in diagnosing some diseases that affect our lungs and our respiratory system, such as asthma, pulmonary fibrosis, cystic fibrosis, and COPD, and emphysema. So spirometry, you can't diagnose it just by you can't just use spirometry alone, but can help and aid in diagnosing these diseases over here. Here we have our spirogram, and we'll notice that in a typical spirogram, it's a graph of time, and it's graphing volume changes over time. So again, this little spirogram, by the amount you blow into this tube, that's going to give a graph of how much, and that estimates how much volume of air is in your lungs. So this is an example of what a spirogram might look like. And what can you get from that? You can get all those different types of volumes mentioned in that previous slide. Now, some of these volumes you can't actually measure directly with this machine over here. So the great thing about spirogram is it gives you a lot of data. It can give you actual measurements of these numbers we see over here. Now, what are the examples of these numbers? Well, there are four main volumes that can be measured. They're measured via spirometry. And these are the four volumes. Now, do I want you to memorize these values? No, because it depends on the study and depends on the textbook. But these volumes, they have definitions. So what are the lung volumes? So the lung volumes are tidal volume. And tidal volume is the volume moving in and out as we're breathing quiet, doing quiet breathing. So we're not using conscious effort to breathe more or less than we normally do. So this is our unconscious breathing. We're always breathing in, inhaling, and exhaling. So the amount that's moving in and out of our lungs is our tidal volume. So whenever you inhale, that means the volume is going to go up because you're adding more volume to your lungs, right? And then as you exhale, that's going to cause a local minimum. So that's going to be when you're quietly exhaling. But again, you're not going to force it past that point because you're doing that unconscious quiet breathing. So just that difference between that, again, so I like to describe it this way. When you're doing quiet breathing, you measure from peak to valley, and that will give you your tidal volume. The peak is when you inhale, when you're doing quiet breathing. The valley is when you're exhaling during quiet breathing. So it's just the difference between that gives you your tidal volume. So tidal volume is roughly equal in women and men, and this is the only one I want you to memorize because it's a pretty easy number, around half a liter or 500 milliliters. So this is one number you should kind of keep in your head. Okay, the next volume is inspiratory reserve volume. And how do you measure that? Well, let's trace it right here. So inhale, quiet, exhale. But notice that now the volume inside the lungs shot all the way up here. So what happened is that you're doing quiet breathing, but then the technician, or you decide to do it on your own, you said, okay, I'm going to inhale as much as I can. And that's why the volume inside your lungs climbed all the way up to here to 600, or not 600, 6,000 milliliters. Now, this is due to forced breathing because now you're making a conscious effort to breathe in as much as you can and inflate your lungs as full as you can. So that's why you kind of hit a maximum over here. Now, how do you measure inspiratory reserve volume? Again, you're inhaling at this quiet volume right here, but this here is how much more you can breathe in past your normal tidal volume. So the way you measure inspiratory reserve volume, or IRV, is you measure from peak to peak. So again, you are inhaling here, but this is forced breathing and a forced inhalation. So you're seeing how much more you can inhale. So you measure from peak to peak. So over here, it would be 6,000 minus 3,000. So in this graph, it would be 3,000 IRV. Now, expiratory reserve volume. So again, like reserve is kind of like if you have cash reserves, that means extra cash you have in case you have like you have to pay an extra bill, or you have a car or bike accident and like, oh shoot, I have to repair it. So something you have on the side that you can use, but you're not going to use from day to day. It's kind of, or just like military reserves. Our military reserves, they're not the front line, but in case we need to use them, that's what we use. Our reserve, our extra. So expiratory reserve volume is our extra volume that we could exhale with forced breathing. So we're still going to, so whenever you have these reserve volumes, they involve these forced breathing, but instead of being inhaling and inspiring, now we're going to exhale and expire. So now we're going to measure, how do we measure expiratory reserve volume? We measure from valley to valley, because again, whenever you have a valley, that means you're breathing out. But with this reserve volume, is how much more you can breathe out. So we're actually going all the way, so we're breathing, this person right here, we took a quiet breath, inhale as much as they can, and then exhaled as much as they can. So this is the maximum they can exhale. So how do we measure expiratory reserve volume? Well, again, this is how much more we can exhale, right? So what we do is, instead of measuring peak to peak, because again, every time you have a valley, that means you're exhaling. You're having a decrease in your lung volume, and you're increasing the pressure, therefore you're exhaling. So with the expiratory reserve volume, you're expiring and exhaling even more. You're trying to force as much air as you can and compress your lungs as much as you can. So do you measure valley to valley? So here's about like what, 2,500 minus, maybe like, let's estimate and say it's like 1,200. So this would be around 1,300 expiratory reserve volume, around there for this graph over here. Okay, so again, it's how much more air you can breathe out. Now, notice that you can't breathe out all the air and you can't collapse your lungs completely, because if you had zero volume in your lungs, that means your alveoli are squashed flat. There's absolutely no air in your lungs whatsoever. But you can't do that normally. So again, you want to keep your alveoli slightly open so it's easier to inflate again. So residual volume is that part you can't squeeze out. You're exhaling as much as you can to get your ERV, but the part that's still left, that's residual volume. So spirometers, they cannot measure residual volume because you can't collapse your lungs. So again, it's what air you can't breathe out. You breathe out as much as you can, but, or like, say you have coffee and there's that, like, and there's like a little like coffee stains and coffee grounds on the bottom of your cup. It's the residue, right? So just like residual volume, it's just like coffee grounds are the stuff that's left over. Residual volume is the stuff left over after you try to exhale as much as you can. Now, with the lung volumes, by definition, again, inspiratory reserve volume, how much more you can breathe in, expiratory reserve volume, how much more you can breathe out, residual, what's left. These lung volumes do not overlap. So by definition, they do not overlap, they can't overlap, but capacities can overlap. And capacities are different, they're related to lung volumes, but they're not the same. So lung capacities can overlap, but the border of each lung volume we see here, and there are only four volumes: tidal volume, inspiratory reserve volume, expiratory reserve volume, and residual volume. So by definition, they can't overlap because the border of one is the border of another volume. Okay, so let's see example spirograms. So this person is breathing and they're doing quiet breathing, and they're not trying to make extra effort to inhale or exhale more than they usually do. So with this quiet breathing, they're actually doing their tidal volume, and we can get this just from regular, normal, quiet breathing. So what we have here is, how do you measure this tidal volume? Well, you just take the maximum and you take the minimum. So during this quiet breathing. So again, every time we have an increase in volume, that means we're introducing more air to our lungs, we're inhaling, and every time it decreases and the line goes down, we're compressing our lungs and forcing air out. So we're exhaling. So tidal volume is just the difference between the maximum during quiet breathing and the minimum during quiet breathing. So I would say measure peak to valley, but it has to be during quiet breathing. So in this case, if we do this measurement, and this would be 500 mils, because you just take the difference between the peak right here and a valley. Now, what happened over here? Well, notice that again, you're breathing in, breathe out, breathe in, breathe out, breathe in, breathe out. But now you're breathing in more than you usually do. So what you're measuring in this case is that we're going to measure our inspiratory reserve volume. Because again, reserve is how much more you can do something, just like your cash reserves is how much more cash you can do. Our military reserves are how much more troops we can deploy. So with our inspiratory reserve volume, how do you measure that? So you measure that by measuring, and this is a common misconception and mistake. Some people, they make the mistake of measuring from peak to valley. But again, it's how much, whenever you have a peak, that means you breathe in. But over here, we did a forced breath in, and we tried to breathe in as much as possible. So for IRV, you actually have to measure peak to peak. So again, for IRV, do not measure peak to valley. You have to actually see how much more you can breathe in. So what we have here is 4,200 and 2,300. So this person's IRV would be 1,900 mils. Okay, now let's look at another spirogram. So here we have regular quiet breathing, but something different happened here. Now, again, every time the lung volume goes down, that means we're exhaling because we're reducing the volume in our lungs. So what happened with this line right here is that they exhaled more than they usually do during quiet breathing. So what we're trying to measure here is the ERV, the expiratory reserve volume, how much more you can breathe out. So in this graph, how do you measure that? It's just like IRV is peak to peak. In this case, you're going to measure valley to valley. So again, for ERV, do not measure peak to valley. Every time you have a dip, you're breathing out. So now you're seeing how much more you can breathe out than normal quiet breathing. So in this case, it would be the difference between these two numbers. Again, difference between quiet breathings, exhalation, and a forced exhalation. So this would be an ERV of 700 in this example. And again, remember that we can't collapse our lungs all the way when we're doing a forced exhalation. Now with spirometry, it can't actually tell you your lung size. And why is that? Because to actually get your total lung capacity and the total volume inside your lungs, you actually need to go all the way from 0 to the maximum during forced inhalation. So because you can't completely collapse your lungs when you're exhaling, and unless you have a pneumothorax, which is very dangerous, don't do that for a spirometry. But the thing is that my point is that you always have that leftover volume, even if you try to squeeze as much air out of your lungs as possible. This residual volume is why you can't actually measure your total lung volume with a spirometer. So if it does have a residual volume, based on your height, weight, and other parameters, they might have an estimate of residual volume, but a spirometer alone can't measure this volume over here. So whatever the minimum is, the lowest point during a forced exhalation, that's the residual volume, where it crosses the graph over there. Okay, so we talked about the volumes. Now let's talk about capacities. So there are four major lung capacities. So our total lung capacity, our vital capacity, our inspiratory capacity, and our functional residual capacity. Now, for these capacities, I don't expect you to memorize the values, average values for all these capacities, but I want you to know how to calculate them given lung volumes and a spirogram. So vital capacity is pretty easy to calculate. So what you do is take your tidal volume and add the inspiratory reserve volume and expiratory reserve volume. But that's not the only way you can calculate it. Just by, if you have a spirogram and somehow you're able to calculate residual volume and total lung capacity, you can actually take the difference between that. I'll show you a graphical example later. Now, for inspiratory capacity, is basically you just take tidal volume and add your inspiratory reserve volume. So this is what you would get if you measured valley to peak. So again, for IRV, you have to measure peak to peak. But if you made the mistake of measuring from valley to peak, you would actually get your inspiratory capacity. So again, it's not the same. And then functional residual capacity. So what you do is it's not tidal volume, but what you actually take is residual volume plus expiratory reserve volume. And total lung capacity is the sum of all the lung volumes. So all the lung volumes, if you take all of them, and again, these do not overlap, but if you are able to add all of them together, you have your total lung capacity. But your total lung capacity is basically what's the maximum volume you can inhale, you can inflate your lungs. Okay, so how can we measure these capacities? Well, let's assume that we have an estimate of our residual volume, and then we're hooking someone up to a spirometer, and we have their spirogram looks like this. So they're doing quiet breathing, and what happened here? Well, their volume went up a lot. That means they did a forced exhalation to increase their lung volume, and then they tried to exhale as much as they could, and then they returned to breathing normally. So the great thing about doing this, just quiet breathing, inhale as much as you can, exhale as much as you can. You can get a lot of these capacities and volumes. So vital capacity, one easy to get a vital capacity from a spirogram like this, you just take the difference between the maximum when you're doing a forced inhalation and the minimum you did with a forced exhalation. So what you do is take the highest peak and the lowest valley, and you have your vital capacity. And look, our inspiratory reserve volume, tidal volume, and expiratory reserve volume, they also fit within that. So actually, I think it's easier to use that as spirogram rather than calculating. I mean, you can calculate either way. So what I'm getting at here is that this vital capacity, you can calculate multiple ways. You can either add all these, the IRV, ERV, and tidal volume, or you can just take the maximum during forced inhalation and the minimum during forced exhalation. So that is your vital capacity. Now your total lung capacity is the maximum you can inflate your lungs if you inhale as much as you can. So that is your total lung capacity if you just take that absolute maximum. But again, residual volume, if you're just using a spirometer, is going to be an estimate. But say you do have your residual volume. Well, total lung capacity is just, and then you're able to get an accurate spirogram using a spirometer. Well, total lung capacity is just the maximum during this graph. It's very easy. And another way to get your vital capacity is, hey, if you take TLC, your total lung capacity minus residual volume, you can get vital capacity. So this is the great thing about these lung volumes. You're actually able to play with the math a bit. As long as you have the correct calculations, then that's the end goal here. Now, total lung capacity. So notice that total lung capacity, common thing that trips people up is that they think vital capacity is the same as total lung capacity. Total lung capacity actually includes residual volume. Again, to get the maximum over here, you need to have everything from 0 all the way to the maximum. So that includes our residual volume. So total lung capacity includes all 4 lung volumes. Vital capacity only includes the ones we're able to measure using a spirogram. Now, what we have here is that there are differences between males and females in their average lung capacities and volumes. And if you compare them, again, tidal volume is roughly the same, easy value, that's the only one I expect you to memorize cold. But the others, what we notice is that all the other volumes and other capacities, males on average have a higher volume than females. So why is there that disparity? Why do males have generally larger volumes and capacities than females? Well, it all deals with volume. And what dictates our volume in our lungs? So our body size also is correlated with our size of our lungs. So the bigger you are, the bigger your lungs are. So here we have a bunch of people like going from shorter to taller. Men on average are taller, but again, this is the whole reason behind it. If you have a larger body, you have larger lungs. So taller people have more lung capacity. So does that mean all men have a larger lung capacity than women? Well, again, it depends on their size. Like if you have me compared to like a 6'4" volleyball player, she's probably going to have a lot more lung capacity than 5'6" me. So again, taller people have more lung capacity, and it's just because on average, males tend to be taller than females. That's why we see a difference in those averages. The other thing is that remember that the movement of air across our vocal cords causes speech, right? Well, this study here says that they had people, they didn't know what the other person on the other line looked like, but they could distinguish between tall and shorter people based on their voice somehow. And yeah, so it's also interesting that even just our lung size can also affect the tone of our voice. And again, our lung size is a product of our height and size. But is it just about height? Other factors can also affect lung capacity, such as our health. Do we have healthy lungs, or are we suffering from something like emphysema or fibrosis or COPD? And also our environment. So if you're living at different altitudes and pollution, or if you live in somewhere that's very polluted and damaging the elasticity and how much your lungs can inflate, that can also affect your lung volumes. So what else can affect lung capacity? Well, fitness can. So here we have, say we have this example. Well, this person, they're lean, but they don't work out a lot. And then person number 2, even though she's female, she works out a lot and she does a lot of aerobic activity, and her respiratory muscles are used to expanding and compressing her lungs to greater amounts. Well, that can also increase your lung capacities and volumes. So better aerobic fitness and just fitness overall, that can also increase and affect lung capacity. And this is anecdotal, but another thing that can affect lung capacity is vocal training and breath control. Now, why do I say anecdotal? Because I'm trying to find a peer-reviewed study about this. But if you're skilled at singing and you're able to sing at a large volume, that requires a lot of good diaphragm control of your respiratory muscles and intercostals. And just remember one time during in-person lab, there was this. She was like, what, maybe like 5'3", but very lean, very slender. But she beat out volleyball players in lung capacity, and then she's like, "Oh yeah, I can sing. I'm classically trained. I'm vocally trained, and I can sing. I can belt out Whitney Houston." So she had really good controls. Maybe she wasn't like super like ripped like this woman over here, but by having a lot of control of the muscles that control her lungs, she was actually able to move huge amounts of air in and out of her lungs through her vocal training. So lung capacity isn't just about size, but it can also have other factors as well. So spirometry can measure a lot of things, but one of the other things it can measure is respiratory rate. So respiratory rate, and why is that important? Well, it's one of our vital signs. So here's a hospital monitor, And here is an example of what you can see on the hospital monitor. And respiratory rate is one of those vital signs you can see on the monitor. Now, again, what are vital signs? Pulse, blood pressure, respiratory rate, and body temperature. But now let's talk about this vital sign. So how do you measure respiratory rate? Well, the way you measure it is just determine how many cycles of inhaling and exhaling happen. So the way you inhale and exhale is some change in your lung volume. So spirometry can measure respiratory rate. So here we have a sample spirogram, and say we take this minute mark over here and measure the amount of breathing cycles we see in 1 minute. So like notice that we start with inhaling. So every time inhale, exhale. So this would be one breath, right? So one cycle of breathing. And if you count how many there are what, 14 of them over here. So 14 breathing cycles per minute. So this is the way we measure respiratory rate. So we measure it by doing breaths per minute. You don't necessarily need to use spirometry. You can measure respiratory rate by just looking at someone's, like if someone's lying in bed and you see their chest rise and fall, you can just time it and count how much per interval of 15 seconds multiplied by 4. Or so the normal range of respiratory rate, because all vital signs have a normal range as well, but the normal range we'll use for this class is 12 to 20 breaths per minute in a resting adult, so resting healthy adult. And it does change with age, so children have a generally higher respiratory rate, but again, this is a pediatrics course. And it can be measured multiple ways. So it's not just spirometry. All you have to do is just see when someone inhale and exhale. Say someone's in a hospital bed and you see their chest rise and fall. That is a breathing cycle. So you can just measure the amount of times that happens in 1 minute, or you can cut it, or you can measure over 15 seconds and multiply it by 4, or do some sort of math, like if you don't want to wait the whole minute. But you don't need a spirometer. That's what I'm getting at. You're just measuring a change in someone's breathing and seeing how many times they do an inhale and exhalate cycle of inhaling and exhaling per minute. Now, if you have so again, our normal range is 12 to 20. Say someone's respiratory rate is above 20. We call that condition tachypnea. So that's a abnormally high respiratory rate. So whenever you see that prefix tachy, that means a faster than normal rate or above normal rate. And then Brady is the opposite prefix. So Brady means slower than normal. So abnormally low respiratory rate would be dipping below 12. So this is why respiratory rate is very important, and this is the way we describe abnormal respiratory rates.